Okay, so let's take a few seconds to scan for the attendance, and then we shall begin once again with our class. All right. All right, welcome again, everyone, to our class. It's yet another week again. I really do hope you are fine and you're well wherever you are listening to this class from, or wherever you're attending this class from. All right, so the last week we have completed the entire topic 3, and we have had one assignment last week. I believe this is your first video assignment. So far, anyone has got any problem with the assignment, or you find it too easy or too hard, or you haven't started? Anyone want to say anything before we start? All right, so it's okay. So if you have any problem at all, I want to let you know that the difference between you watching YouTube and you attending this class, here's the difference. The difference is that you get my tutoring and you get my mentoring. So that is what YouTube or any other videos out there cannot give you. So I really do hope that if you face any problem, you would reach out to me. Yep. So other than that, if you do reach out to me, I will try my best to help you. But if you don't, I really don't know what else I can do. So I'm trying to help you as much as I can with all the resources I currently have. All right. So that is about assignment. And today we are going to continue with our class. Let's proceed on to next slide. Let me see. Okay. So this week we are officially going to start our brand new topic. This is topic 4. Topic 4 will be one of the most important topic I can recall. Yeah, if you can only understand one topic from this entire course, it is topic 4. So I highly encourage you guys to invest your time to understand this topic 4, because in the upcoming topics, topic 5, 6, 7, and 8, we are going to take what we gain from topic 4. If you don't understand this topic 4, then you are going to have a really tough time with topic 5 and above. So if, yeah, so that is topic 4, and we are going to use about 2 weeks to cover topic 4, and then we'll be done with this. All right, so in today's class, we are going to cover the preliminaries of topic 4, which is Boolean algebra. So in the last topic, I believe I've talked about Boolean algebra a little bit. So Boolean is like Boolean is like a person, like his name was George Boolean, and he was the one who invented this entire Boolean algebra thing. And as a result, like, we all need to study this. All right, no good. Okay, just kidding. All right, so Boolean was the guy, a scientist back then, who invented this thing called Boolean logic. And if you recall, in Boolean logic, there is only 2 possible situations. So it's either a yes or no. There's nothing in between. So that is what this course is all about. That's why I call it digital logic. So in digital logic, we use Boolean logic, and we also have something we call Boolean algebra. Okay, in the last topic, topic 3, we've seen something we call Boolean expression, right? So Boolean expression is a mathematical expression using Boolean laws or Boolean logic. Okay, so in this topic, we are going to dive deeper into what exactly is this Boolean logic, Boolean expression, and today we have Boolean algebra, right? Good news is that it's not too far off from the algebra that you know. And I would say that it is 100 times simpler to do Boolean algebra than the algebra that you have done in the past. So in today's class, we are going to take a look at Boolean algebra. All right, let's start. Okay, so to first begin this class, in Boolean algebra, so just like in normal algebra, right, you have a lot of laws that you use. Okay, a law where you can factorize You can factorize the terms out, a law where you can multiply. There's so many other algebra laws, right? If you recall from your previous courses. Now, same thing with Boolean algebra. So these are the laws of Boolean algebra that I think it's important to know. And good news is that it's going to be pretty much common sense. But I'm going to highlight this common sense to you in a Boolean algebra context. It's going to be slightly different. Let me show you what is this. Okay, so these are the rules of Boolean algebra in short. Okay, so that we will go through every one of these rules very quickly in a bit. And then I really hope that you guys can really understand what this rule is all about instead of memorizing. Actually, in my class, I really discourage you guys to memorize any kind of thing, especially this kind of formula, which looks like it doesn't make sense. So I will highly encourage you guys that before you memorize anything at all, try to understand it, because the moment you understand it, you don't even need to do any kind of memorization because you understand it, the fundamental of it. Okay, so these might look like it's alien language right now, but by the end of today's class, this will be like super crystal clear to everyone. Okay, let's dive in. Okay, so let's first add this first law. Okay, so this first law, wait, well, let me see why my slide is a little bit jumbled up. Okay, never mind. Okay, so in this first law is known as the commutative law. And in this law, we can see that there's two expressions over here. So the first one you see on top, a plus b equals to b plus a. Okay, same thing over here. Okay, even though it might look like it's common, it's like who doesn't know a plus b equals b plus a? But the one thing I want to highlight to everyone here over here, is that whenever you look at this kind of formula, instead of thinking in terms of addition or multiplication, so I find it easier if you think in terms of logic gates. Okay, in terms of logic gate, then it makes sense. For example, over here, right, we are seeing here a. It's not a plus b, but it is a or b. Okay, think in terms of logic gates. So if you cannot think why is it or, so you can think about it in this way. So if I have an or gate like this, or gate, so if I have a or with b, and if I have b or with a, so are they the same? It obviously is the same, right? Because this is the same component, it's the same wiring, it's the order is different. Okay, so for every expression, I would like everyone to think in terms of logic gate, and then things will be easier. Okay, so as we can see over here, a or b is equal to b or a. So same thing over here, we can see that we have a and with b is exactly equals to b and with a. So it's just swapping out the order. The order does not matter over here. Okay, right. So if you draw out the logic gate, it looks like that. So it's exactly the same. That is one. Okay, that's one done. I mean, that's actually two done. So these are a couple more laws that I will go through very quickly. Let me change my pointer color so that it's easier to see. Okay, change to green. Okay, so these are associative law. Okay, for example, what is associative law? So this is the formula, the law for this is the associative law. What it says is that so if you have a, and then you add with a bracket b and c is equals to ba. But this bracket can be over here instead. Okay, so yeah, this is also kind of like common sense. It's no different from the usual algebra law that we have like before this. However, I would like to invite you to think in terms of logic gates, right? So think in terms of logic gates. So if you have a, is a over here, and or with b or c. So b or c is at here, at this point, and the output is going to another logic gate, and then that logic gate is going to or with a. Okay, so that is on the left side, and on the right side. So we see the way we draw the logic gate is slightly different, but the outcome is the same. Okay, so you can see over here there's a one OR gate over here, the other OR gate over here. So firstly we OR with this bracket, so we OR at this, and then we get an output over here. This is an intermediate output, and then this output you OR it with another term, which is C. Okay, and then you get your output. Okay, and it also works with AND. So you have AND gate. We call this cascade. Okay, we call it cascade. So if the AND gate is cascaded in this way, so it means like A. So we have an A, and then we over here we have a multiplication. Where it's not explicitly written A, and we AND it with B, C. Okay, B and C over here. So that is how we draw this following this bracket. Right. And over here is the same thing. If you place the bracket A, B, the outcome is the same. So when I say the outcome is the same, it means that the answer here and the answer here will be the same. Okay, no matter how. Right, so those are some simple ones. All right, so next we also have this distributive law. So distributive law is like a fancy name, like I think we've done this before. So if you have a algebra expression that's like so, okay, so you can actually expand this into this. On the left hand side, you multiply this a times b and multiply this a times c. This is the expanded version. Okay, this is the expanded version. So the law says that this in logic gate is also the same in value with this in logic gate. However, if you really to draw it out, you see that, okay, even though the drawing looks different, one on the left hand side you have 2 gates, on the right hand side you have like 3 gates, but the output here is the same in value as the output over here. Okay, so don't be deceived. You see like, okay, so this drawing and this drawing is like different, so they must be different. No, okay, they are the same because like the expression is the same. Okay, so let's take a look at the next one. All right, so the next one is a pretty simple one. So let's say, so this is the law that I'm going to talk about over here. Okay, so this is where it gets a little bit different than your usual algebra. So let's say you have like a or with 0. A or with 0, if you think mathematically, okay, yeah, it still makes sense. Anything plus 0 is still equals to anything, okay? But if you have like over here, anything plus with 1 is equals to 1. So mathematically, it is no longer beneficial to think it in terms of mathematics in your usual Boolean algebra, in your usual linear algebra. So in your linear algebra of your previous algebra knowledge, because it's no longer the same. So in this case, I'd highly encourage you guys to think in terms of logic gate. Okay, let's take a look at the first one first. So you have A and you have A or with 0, it looks like this. You have an OR gate over here. So you have an A, you have A to be one of the input, and the other input is 0. Okay, so this value of A can either be 0 or it can either be 1. Okay, so let me make sure I make myself clear. Let me just redraw this over here, right? So if you have an OR gate like that, okay, I'll draw this nicer. Okay. Okay, so if you have an OR gate like this, so you have A and 0. So the question is, what is the output? All right, so now the next thing we want to know is that what is the value of A? This value of A can be 0 or it can also be a 1. Okay, let's take a look. If the value of A is 0, what do we get? So we get 0 or with 0, and the output will be 0. Okay, so let's write it out over here. If A is equals to 0 and then I'm going to write here x. Then x is equals to 0. X is the output, right? Now, what about if a is equals to 1? If a is equals to 1, and then x will be, if you put in here 1 and then 0, and you do the operation, it's OR operation, and then the output will be 1. Okay, so what we notice over here is the output will always equals to whatever you give it at the input. Whatever you give it at the A, that is what you find it at the output. So that's why we have over here A, you OR it with 0, whatever value of A, you would get it at the output. Okay, so this is how I would like you to see, to interpret this Boolean algebra. Okay, right. A or with 0, you get an A. So let's take a look at the next one. So if we have another example, what if we OR it with 1? Okay, so we have the same thing, OR gate, right? Now we have A, and we OR it with a 1. Now the question is, what is the value of x? What is the value of output? Okay, now we can have two scenarios again. Two scenarios where A is equals to 0 and A is equals to 1. There's no other value, there's no other possible value for A, right? Digital logic, right? Boolean algebra, you have either 0 or 1. So now let's take a look at what is the value of x when A is 0. So when A is 0, you would get over here 0 and 0, or with 1, you would get x to be 1, okay? Because 1, okay? Now, what about the situation where A is 1? When A is 1, this is kind of straightforward too. When A is 1, oh, of course, x will also be 1. Because like 1 or with 1, you get a 1. So what is the conclusion that we can draw over here? So the conclusion that we can draw over here is that when you have a 1 over here at the input of an OR gate, this value of A does not matter. Okay, why do I say it does not matter? Take a look at this. If A is 0, the output is 1. If A is 1, the output is also 1. Okay, so that is the situation that we have over here, and that's why coming back over here in this term, we see that if you have A and you have a OR with 1, so it doesn't matter what this value is, the output will always be a 1. Okay, that is a fact. You cannot change that. Okay, so maybe some of you might be thinking, wait, why am I using this A? Can I use other letters? Yes. So A is just an example. Okay, you can use B, you can use C, D, or whatever letters that you like over here. Okay, so the point is this can take two values, either 0 or 1. Okay, so these are the some of the rules over here that I hope you are beginning to see. Okay, this is kind of like common sense. You don't need to memorize this. A or with 1 is 1. Okay, so think about it in terms of this logic gate, and this will make sense, right? Okay, next. Okay, we see just now we had an OR gate. Okay, now we have AND gate. Let's see what's the difference. It's actually quite similar though. So we see that A and with 0 is 0, and over here same thing. A and with 1 is, yeah, you get A. So you can think about it, you can think of this mathematically. So mathematically it makes sense over here. A multiply with 0, of course you get a 0. And A multiply with 1, of course you get the same value again, you get A again. Okay, however, as you have seen in the previous example, not in every situation you can think about it in a mathematical sense, because it's slightly different when it comes to Boolean algebra. Okay, so I would highly encourage you guys to think in terms of logic gates as well over here. So if you have an AND gate like that, and you have three inputs, two inputs and one output, and one is always 0 over here, and then the question is what's the output? Okay, so like A over here. So now you can see over here that it doesn't matter what I give into this A, 0 or 1, the output will always be 0, because I have this culprit over here. I have this 0 constantly feeding into my logic gate, so X will be 0 regardless of my value of A. So that's why we have this rule over here. anything multiply n with 0, you will always get the 0. Now, same thing over here. We have that also x, and we have 1 over here. So take a look at this again. It doesn't matter what I give. I give it to this value of a. My output will always equals to a. Okay, let's dive in deeper into this. So what does it mean by that? So you see that if I give a value of a 0 to a, so when I have a equals to 0, now what's the output? The output would be 0, and with 1 you get 0. So when a is equals to 1, so I give it a value of 1 into this gate. Now my output here will be x equals to 1, and with 1, then I get a 1. So the conclusion over here is that the output is always equals to whatever I give the input at the a. Okay, because you have 1 here. So that's how we get this rule over here. Okay, so far so good, right? If you do have any questions, feel free to just type it in the chat. All right, so yes, over here it gets slightly more, a little bit strange. Okay, let's bear with me. Okay, so over here we have a plus with a equals to a. Okay, so this is the situations where if you use your normal linear algebra knowledge, this is wrong in linear algebra. So in linear algebra, a plus a, you're supposed to get 2a, right? Okay, so it's not that is not applicable over here because we are dealing with Boolean algebra. So that's why I said in the beginning that it is very beneficial to think in terms of logic gates. So let's take a look at what we have over here. So we have a, and we OR it with a. Okay, so let's put this in terms of logic gates. So we have two cases, case 1 over here, and we have case 2, case number 1 and case number 2. Okay, so case number 1 is that when a is 0, what happens? So when a is 0, both of these will be 0, and then the output will be 0 because you have 0 or with another 0. Get the output 0. So in the second case, you can also have a situation where a is 1. So when you have a is 1, so over here we have 1 logic high, or with another logic high, the output will be high or low. The output will obviously be high. Okay, high. And there is no such thing as 2 at the output. Okay, remember it's either 1 or 0. So that's why in this case you have a, or with another a, you get back the value of whatever you give it at the input. If you give the input 0, the output will get 0. If you give the input 1, the output you get a 1. Okay, so that is this rule. A plus a is a. Okay, let's take a look at the other one. So this is also slightly related. Let's take a look at this. We can also have this a plus with a bar. Okay, so this apostrophe here, it stands for bar. Okay, I can there's two ways to write it. You can write it like this, or you can write it a bar like that. Okay, so in books, usually I think in books you will see this. In websites you will also see this form. But if you see this, you know that it's a bar on top. So I would prefer this one because it's, to me, it's easier to see. Okay, it's very hard to miss. Right. So let's take a look at this. If you have a and a bar, what happens? Okay, so let's think about it in terms of logic gates again. So you have an OR gate over here. Now over here we have a, and over here we have a bar. Okay, so let me redraw this so that it is a little bit clear. Same thing, we have case 1 and we have case 2. Case 2 over here. Okay, so let's take a look at here's a, and here is a bar. So what is x? So let's take a look at case 1. So whenever we have a to be 0, so which means I have here 0. Now, if a is 0, then a bar needs to be 1. Okay, because it's a bar. Bar means it's the inverted version. Okay, it's a It's a complement. Okay, so it's an inverted version of A, so it's got to be 1. And then what is the output? The output will be 0, or with 1, then you get a 1. So let me write this in this form over here. If A is equal to 0, A bar is equals to 1, then here my x will be equals to 1. Okay, now let's take a look at case number 2 as well. Case number 2. So instead of A 0, now in case number 2, A here is equals to 1, and A bar, okay, A bar is the inverse of 1, so that will be 0. Now over here we have 1 or with 0. Again, it's 1 or with 0, and then it will be 1 again. So let's write this down here. If A is equals to 1, then A bar is equals to 0. This gives me the output of x is equals to 1. So what I want to highlight over here is that when you have this situation, you have OR, and then you have a variable, and then you OR with another variable inverse, you always get the value of 1, okay, regardless of the value of whatever value over here, okay? But the trick is this two must be the same variable, okay? So it must be like this, okay? It does not work like this, okay? Like this b is another variable, is different value, okay? So it only works if they are both of the same variable. Can be a. If you have b, then this got to be like this. And if you have c, I think you get the point, right? C, you get the point. This two must be the same variable, and one is the complement or the inverse of the other. All right. So that is this one. So I hope things are making sense to you right now when you think in logic gates. Okay, so the same thing, we can have the similar idea in AND gate as well. So in AND gate, if we see that A dot with A, or A and with A, you get A as well. Okay, again, this is it doesn't make sense if you think about classical algebra, because this is Boolean algebra. So how to make sense of this is to think about it in logic gates. So if you have an AND gate over here, and you have 0, there are two cases again, case 1, and then you have case 2. Okay, so I'm going to go a little bit quicker because I think you already get the idea. So case 1 is when A is 0. Now the output you get 0. When A is 1, the output you get a 1. So the conclusion over here is that whatever you give it at the whatever value you give at the input, that is the value that you will find at the output. Okay, because when A is equals to 0, then you get x 0. Okay, I'm taking x as the output. Okay, so whenever A is equals to 1, and then my x is equals to 1. Okay, so that's why A and with A, you get the whatever value that you give in A. Okay, same thing. If you have AND, but this time you end it with the complement of A. Complement of A. So what it means is that in case 1 and case 2. So in case 1, when the value of A is 0, now over here is the second input is the A bar, the inverse of A. So that means that the second input is the reverse of whatever value you give over here. So if it's 0 over here, then it's got to be the reverse, which is 1, and you get a 0 at the output. Now in case 2, this time A is 1. Now, because A is 1, A bar is got to be the reverse of 1, which is 0, and the output will be 0. So in this case, we see that if you have A and you end it with A bar, it doesn't matter how you do it, the output will always be 0. Okay, it's like multiplying 1 and 0, and then 0 and 1. That's how you get 0 at the output. Okay. All right, so the other one would be, this one is also common sense. You have double bar over here. So A apostrophe can also be written as A bar and bar. So if you think about it in logic gates, again, if you think about it in logic gates, there's only one way to think about it that is using logic gates. That in classical algebra, you don't have this kind of thing. So double bar means a double inversion. So a double inversion means you go through a NOT gate and then you go through another NOT gate. So which is what you are seeing over here. Okay, so you go through one NOT gate, the value reverses once, and the value go through another NOT gate, it reverses again. So you get back the original value. So that's why what you're seeing over here is a double bar is also equal to the original value, which is a. Okay, so hopefully things start to make sense over here when you start to think in uh, uh, logic gates. Any question? Let me take a drink. So far, okay? All right.
Okay, sir.
All right, thank you. Thanks for your response. It's kind of boring, you know, like I'm talking to a PC. I don't know. It's like talking to a wall. So sometimes if I get a response, it'll be like, it's really good. Okay, right. So we are nearing at the end of our list of laws over here. And the next one, we'll see that, okay, this one is going to be slightly peculiar. It's going to be slightly weird, as we see over here. So this is what the law says, Boolean algebra laws. And okay, let's take a look at it mathematically. Mathematically, if you use linear algebra and try to interpret this mathematically, I think it's hard to make any sense of it. Okay, but again, if you try to draw the logic gates, yes, you can draw the logic gates, and you will find that they are equal. Okay, but in this slide, I'm going to show you how this can make sense if we use Boolean algebra to do the calculation. Okay, so over here we are seeing a. We are seeing a. How in the world do they get this thing a over here, right? So let's take a look at it over here. This thing a is okay. Let me mark this. A is over here. Is this equal? Because from previous law we know that a, anything you end it with one is just a, right? So I can write it like this, and I'm not even changing anything on the expression. Okay, so it's the same, equal in value. Now, what I try to do next is I try to factor out the a. Okay, over here, I can do this a, and I factor out. I have 1 or with b. Okay, actually, like even if you don't do this, you can just factor this right out. So factorization works the same way. Okay, factorization works the same way. You can just factor this one out, get 1 or with b, like that. Okay, if you can factor this out immediately, you end up here. So what is interesting over here is that once you arrive at this second step, now we see that over here we are seeing 1 or with b. So remember just now, if you have 1 and then you go through an OR gate, 1 over here, and then you have b over here, what is the output? The output will always be a 1. Whatever you give it, you don't care whatever this value of b, because if b is 0, the output is 1. If b is 1, the output is also 1. So that's why we are seeing over here, oh, we have 1 or with b, and we know that this one is actually a 1. 1. So that's how it ends up over here. A multiplied with 1. And we know that if you have a, you have AND gate 1, you always get a. Okay, so that is how we ended up getting this. Okay, so again, over here, I am using this A and B letter. So do not be confused. If suddenly I change X and Y letter, can I do? If I have X, Y. So what would the answer be? It's gonna be X. Okay, so the key is this variable and this variable has got to be the same. Okay, and this variable can be something else. Okay, can C and CD. Okay, we get C. Okay, so hopefully you get the idea. So these letters, they are just placeholder. It doesn't matter what kind of letter they use. Okay, so that is how this thing can make sense. A plus AB is equal to A. Okay, right. Next, we see the next one over here. A plus A bar B is equals to A plus B. Okay, again, it looks like it does not make any sense over here. Let me write this down. Bar B. Okay, how in the world would you get this? Okay, this is a mathematical proof over here on how do you get that. Okay, so we see that A and A plus AB, are they the same? From this previous law over here, we see that they are the same. A plus AB is A. So what I'm doing over here is that I'm rewriting this equation. So A plus AB, and they are now they are actually the same thing. This is actually still A. Okay. Now, and what I'm doing next is this one is still the same over here. I didn't change anything, and I have A. Then we can do something, and we immediately we see that okay, there is something that we can do over here. So let me rewrite this line out. You have A like that, and then you have plus A bar B. Okay, so immediately we see there is a common term over here that we can factor out, and the common term is B. So what I want to do over here is I factor out this B, and I have this A plus A bar. Okay, now this is something that we would like to see, because this one, you know, right? A or with A bar, like you know that this one must equals to 1. So then we have this like this 1. Okay. And then that is how we end up with if we have 1 and multiply with B, so you would always get a B. So that's how we end up over here. Okay, so is everyone okay still? Not sure why I cannot erase my inks anymore.
Sir, I have a question.
Yes, please.
For the answer for the second equation, does the only answer is A plus B, or is there any other form of answer other than A plus B?
Okay, so there can be other form of equivalent answer. Okay, so because as I've shown you in the previous slide, right? The two circuit can be different, but they can produce the same outcome. Okay, get what I'm trying to say over here. Okay, for this this particular case, this is the only answer, I believe, unless you can come up with another answer. That's why this one becomes the rule. Okay, rule or the law. Okay, but it's not always like this. In some situations, you will have some other answer, and even though the answer is different, but if you draw the logic gates and if you make the truth table out of it, you would find that they are the same truth table. The truth table can be the same. Okay, does that answer your question?
Yes, sir. Thank you, sir.
All right. Okay, thank you for asking. At least I'm not too bored, right? Okay, so that is how we arrive at this A. Okay, over here. So this one, maybe I leave it to you to remember or memorize if you would like to. All right, next, take a look at another one. Okay, so okay, I promise this is going to be like the last mathematical derivation that we have over here. Okay, so we see that we have over here A plus B and A plus C. They are both in the bracket, and the outcome would be this. Okay, this is the most simplified version. So this expression over here can be simplified into this one. So how is the simplification done? Why is my slide? Okay, how is the simplification done? So it is like here below. Okay, so in Boolean algebra, what we can do is also do expansion like that. Remember this multiplication with the bracket? Okay, so we can do the same over here as well. And if we do this expansion, we'll get A multiplied with A, which is this term, and we get A multiplied with C, which is this term, and you can do B multiplied with A, which is this term, and then you can get B multiplied with C, which is this term. Okay, some of you might ask me, okay, so B multiplied with A multiplied with B, is it the same? Yes, it is the same. Okay, the order does not matter again. Now, that's how we got the first line here. So what is next? We see that, okay, there is something that we can simplify over here. For example, A and with A, we can simplify it into A. Okay, so think about it in terms of AND gate over here. If A and with A, so the outcome will always be A. This is what we've covered in the previous law, remember? So we can simplify it like that, A. So AC, nothing to simplify, AB, nothing to simplify, BC, nothing to simplify. That's how we arrive at this second line. Okay, now, then next we see that, there is like a common term that we can factor out. Okay, so the common term that we see over here is, there's A over here, and there's A over here. Okay, and there's also A over here. And okay, so what we want to do is to factor out the A, and the objective of why we want to factor out is to get this cute little guy over here. Why do I say that? Okay, so let's try to do this factorization, right? So I can factor this out like so. I can have 1 plus C, like that. I can factor out this way, but I can also consider this one in, okay? Because this one also has an A, right? Plus with B, okay? Plus with B, C. Okay, I can do the factorization like this also, but that does not help me simplify the equation, because at the end of the day, I get this, A, C plus B, like that. And it doesn't do me any good. The equation is like no different from the previous one. Okay, so that is why you are seeing over here, instead of factorizing it like this, what I'm doing over here is factorizing it like this. Okay, so I am leaving this one out of the bracket. So I do the factorization only for 1A, and then it's only for this. Okay, and the reason is because I want to get this one. Okay, because we know that if I have this one, then it will reduce my complexity. Okay, because we know that 1 or with C, you will always get a 1. That is how you get the next line over here. Okay, so the next line over here is A. So this one is multiply 1. So you get that, the same answer. And you have AB and BC, they are the same as before. And now, just like previously, we can, so I'm rewriting this over here. A plus AB plus BC. Okay, hopefully now it's clear. Now, can you see any common term right now that you can factor out? Okay, I have B over here. I have B over here. Can I factor out the B? Yes, I can factor out the B. No problem with that. But does that do me any good? It doesn't help me. It doesn't help me simplify the equation. But we have over here something that we can factor out. So we can see A, factor out this, we get 1 plus B. Okay, again, this is our favorite thing to see. Okay, because we know that if you have this, then we know that this one is going to be 1. Then we have this BC. So that's how we arrive at this. Okay, and that's how we arrive at this answer. Okay, so hopefully that makes a little bit of sense to everyone, because using these principles that I have outlined in this slide, in this few laws over here, we are going to begin solving Boolean algebra like after this, and you're going to see how fun it is to actually solve this. It's like, trust me, it is very satisfying to be able to solve this Boolean algebra. Okay, you know, it kind of makes you feel like a genius. Like, but in real fact, it's like very simple. Okay, so before we dive into solving Boolean algebra problem, like there's one more theorem that I want to highlight to you guys, and that is called De Morgan's theorem. So De Morgan's theorem is another simple thing that you might want to remember when you're solving Boolean algebra equations. So this is what De Morgan theorem says in brief. So if I were to draw this out in logic gates, I would get something like this. Okay, so this is a multiplied B, that's AND gate, and if you put a bar, this becomes a NAND gate. Okay, and this is equals to, this is a NAND gate, and this is also equals to this. You have A, you have invert A, or with invert B, and then you have something like this at the drawing. So does this look very familiar? Remember in the last topic, I showed you that a NAND gate is actually equivalent to a negative OR gate. Why is it equal? So I showed you that it is equal because the truth table is the same, exactly the same. The truth table for NAND gate and negative OR gate, if you're to list out, they are exactly the same. So with the one principle that I want to outline, I want to give over here is that if the truth table is exactly the same, it doesn't matter how the circuit looks like. It doesn't matter how the drawing looks like. It is the same because the outcome is the same. Okay, so just bear that in mind. This is what the De Morgan theorem. De Morgan theorem is just a mathematical form of this. Okay, this drawing over here. So the way that I remember De Morgan theorem is very easy actually. So for De Morgan theorem, whenever you have a bar like this, right, and if you want to break the bar, you have to change the sign. That is how it goes. I have a bar like this. So if I want to break this bar apart, I have to change the sign. So let's say I break the bar, I break it into the individual component, breaking the bar. This is breaking the bar. So once I break the bar, what I need to do is to change the sign. What's the sign? So over here, the sign is actually a multiplication. It's not explicitly written out. And from multiplication, you want to change it to addition. Okay, addition. So this is how I remember De Morgan's theorem. You can remember it this way, or you can choose your preferred method to remember this. Or you want to remember this drawing, that's De Morgan theorem also, right? Feel free to do so. But point is, they are equal, they are the same because the truth table is the same. That is De Morgan's theorem. So this is also De Morgan's theorem. Now this time, it's the same thing, De Morgan's theorem, but right now the bar is like a little bit different. So you have A plus B instead. Previously we have A multiplied with B, right? So we have A plus B, and then you have a huge bar over the both of the term. So what you want to do is you can break the bar into individual components like that. But once you break the bar, you need to change the sign. So from plus sign, now you are going to write this as multiplication. Okay, this is OR gate. Now this becomes a AND gate. Okay, this is how we end up with this expression over here. Again, we can always draw this out in logic gate, and it looks like this. This is a NOR gate, and a NOR gate is equivalent to a negative AND gate. Again, why? Because the truth table, they are the same. Truth table for NOR gate on the left, truth table negative AND gate on the right, exactly the same. Hence, we say they are equivalent. Okay, so that is how we get this De Morgan's theorem. Okay, so now let's take a look at an example, very simple example of simplifying this. So we can apply De Morgan's theorem to this expression. So you have W, X, Y, Z, and you have one big bar on top of here. So what can you do with this is can use De Morgan's theorem, and in De Morgan's theorem you can break this bar up to the individual term. But what you need to do next is to change the sign. Notice here the sign changes. The sign changes. Okay, that is how we can use De Morgan's theorem. Okay, now let's try De Morgan's theorem. Now this time we have it over here. Okay, from this point on, if you have a pen and paper, I encourage you guys take this pen and paper out, like work it out together with me. Because if you don't work it out and you're just taking it from me, then you're going to get very little from this session. Okay, and also sometimes when I'm working this out, there can be mistakes here and there. I'm not perfect also. So if you work it out together with me, we can catch those mistakes together. Okay, so now let's try to do this. De Morgan's theorem. So we have this going to write this. Okay. You can see that we have a big bar on top, right? So what we want to do in this case is, let me write this. So, okay, let me write this as there's a bracket over here and there's a multiplication over here. Okay, so it's the same thing, right? I'm just putting a bracket. It doesn't change anything. Yeah, bracket is even here. I'm just putting a multiplication over here. So what we want to do in this situation is we want to break the bar. But then the question is, which bar do you break? So the idea is simple. We break it from the outermost. So we started with this one. Okay, so the first step would be this one, and then they have a D like that. And inside here you have A, B, C. Okay, so now this one D was a multiplication. Now this one becomes an addition. Okay, this is step one. You break the outermost one. Okay, now then we see that okay, there is this big bar over the entire term over here. We can break that one down as well. Now that's the next thing we're gonna do. So we're gonna write this here A. This time we have bar, C, bar, bracket. This one does not change. Now this one previously was a addition. Now this time it becomes a multiplication. Okay, so then at the end of the day, if you want to write this out more beautifully, it becomes like this. Okay, so that is how we simplify this using De Morgan's theorem. Right, so I have this on my slides as my answer. Okay, so simple, right? Using De Morgan's theorem and simplifying Boolean algebra equation. Okay, so right now we are going to try to simplify a few more examples, and then hopefully after today's class, you guys will be like a pro expert in simplifying Boolean algebra. All right, so here is what we have. We want to simplify this A, B, A. Okay, so what do we do? So we can see that over here we have AB. Okay, there's nothing we can do to simplify this. Now we can have this. Okay, over here we see that there's bracket. Okay, there's opportunity for us to change things over here, and that is to expand this. And there's also opportunity for us to change by expanding this. Okay, so let's try to do that. So I like to write things down nicely so that I don't make mistakes. So I have AB, then I do this expansion first. Let's try to do the first expansion. A multiplied with B, I have AB. A into C, I have AC. And then next, I have over here B multiplied B, I have B. Okay, B multiplied with C. Okay, C, I have BC. Okay, now it looks like we are arriving at a much more complicated equation over here. But there is good news, because why? Do you see what I see over here? There is like a magic common term that we can factor out together over here, and that is here. Okay, so if we try to do this, okay, the rest we don't care about the rest first. Let's try to just B plus AC. Let's try to do this one first. We tackle this one by one. We can factor this one out, and then we have 1 plus C. Okay, which is good news. This is something that we are so looking forward, because we know that this entire term is actually just 1. Okay, 1 or with anything, you get a 1. Okay, so at the end of the day, you get AB plus, okay. The other thing that we see over here is that AB and AB is repeated again. Remember, previously we had A, what is this? Is this 2A? No, it's A, right? It's the same. Well, here it's repeated, so I'm going to write it once, AB plus AC, and then plus B. Okay, B multiplied with 1. Okay, but I'm not going to write this 1. Okay, the same thing. Okay, now we see that is there any other opportunity for us to factorize things so that it's equal?
AB plus B can factorize.
Yeah, see this one, and look at this single term over here, right? So you can just factor out this B, and then you can have 1 plus A. Okay, and I keep the AC term, so this term is the same over here. Okay, this is again good news. We know that this is 1, so I'm just going to write this as B over here, and then that's how we get B plus AC. Any other term we can change over here. So this is as simple as gets. I don't see any way anymore, any way forward other than this. Okay, right. So the next question, we have arrived at this as our simplified answer, right? And the question is this and this, are they equivalent? Are they equivalent? So the answer is, if you try to make this, draw this out, this is what you get on the left. You draw it in logic gates. Okay, so you can track this A B. This is A, and then A, and then this is B. Okay, this is A B, and then you draw everything out. This is what you get. But draw things out, the things on the right, you get this one. So if you were to make the truth table for these two logic gates combination, are they the same? Yes, you're going to end up with the same exact truth table, except that in one case, there's a whole ton of logic gates over here. 1, 2, 3, 4, 5 logic gates. And over here, we have only 2 logic gates. Okay, 2 logic gates. But they are equivalent because they produce the same truth table. So how is this useful? So in the industry, you can see that if you have a computer, this computer uses 5 times, let's say, okay, it's a very simple computer, it uses 5 logic gates. And over here you have the same computer, but it can run only using 2 logic gates. So that's like 50% reduction, okay? More than 50% reduction in the materials, but they produce the same result. So that is why Boolean algebra simplification, that is how it can be useful when you want to implement a logic system like this, right? Okay, so let's try our hands on a few more examples and then we'll end our class today. Okay, so let's try this one. So this one is going to be a little bit more challenging than the previous one because we have like a giant bar. So know that every time you have a giant bar like this, you can always use, yes, you've guessed it, De Morgan's theorem. Let's just try to use De Morgan's theorem on the first one over here. All right, so we have over here big bar. I'm going to break it into smaller bar like that. Smaller bar like that, AB and AC. Okay, this bar goes to the individual terms, and now this one changed to multiplication. I'm going to put a bracket over here so that I don't mix up later. And A bar, B bar, C. Okay, nothing we can do on this second term. Now, let's try to do this again. Now we still see, okay, there is like this bar over multiple terms over here. Can I break that? Yes, we can always break that. So we can break that like that, and we can break it like so. But then we have to do addition. Okay, and then over here there's a multiplication. So let me put a bracket over here so that I don't mix up. Okay, right, so I'm going to do the same for this, A, C, and then I'm going to change this sign. Okay, and the outer one, I don't see any difference. Okay, clear? Now, we see that we have an opportunity to expand things inside here. Okay, so let's try to do that expansion. First thing, multiply this. A bar, multiply with A bar, you get A bar. Okay, next one, A bar, multiply with C bar. Get this, let me put the bracket. This A bar multiply with C bar, you get A bar and C bar. And then next you have this one, b bar multiplied with a bar, b bar multiplied with a bar, b bar multiplied with a bar. Okay, and next one we have b bar multiplied with c bar. Okay, b bar multiplied with a bar. Okay, double check the workings. All right, so the outside term, they are same. Okay, now do you see what I see? So there is an opportunity inside here to make things simpler. So what is that? And that is to do some factorization on some common terms. All right, so what are the common terms that we see over here? So we can factorize out this a bar over here, and then we can factorize this out. Okay, let's try to do that. A bar, and now you have 1 plus b bar, like that. So you have b bar, a bar. Okay, actually, you can include more terms inside there. Okay, but we're gonna take it one at a time. Okay, all right. So we know that if we do this, this one will be 1. So I can rewrite this as just a bar, remember that, bar, a bar, okay, plus b bar. Okay, now we see that there is another opportunity over here that you can factor out this one. Okay, actually you can include this term early on if you like. Okay, if you include this term early on, if you, that would be a bar. You have 1 plus c bar plus b bar. Okay, and this entire term would just be 1 because there is a 1 inside, right? Okay, so it doesn't matter which way you do, you would still get a bar plus, so I'm gonna do this second factorization out, 1 plus b bar. So this one is also equal to 1 plus b bar c. Okay, I need to remember to write this outside term. Right, like so. Okay, so then I simplify this by writing just a plus b bar, that, and plus a bar, b bar, c. Okay. So far is okay. So let's see what other opportunities that we have over here. Okay, so I can just remove this bracket, right, because there's no multiplication involved, right? So we can see like the same thing. So we can factorize this a out and this a out over here. So we can just do this a 1 plus b bar c, and you can plus it with b bar c bar. Why is it not showing properly? Plus b bar c bar. Okay, and we know that this is 1, and your final answer you would get a bar, b bar, c bar. Okay, so this is the final answer. Is everyone, are you doing okay with this? It makes sense, right?
Sir,
Yeah.
how did can I ask how did you factorize the a bar at the last step? I lost there.
Okay, here, right? So can you see the common term over here? Here, and here. Right, can you see how we can factor this out? If I were to rewrite this, okay, let me rewrite this somewhere up there. I'm just rewriting and reordering this. Same thing.
I see, I see.
Okay, same thing, right? So that's how I get the ordering, the factoring out. Okay,
sir, thank you.
right? Anyone else have any question? This is our answer right here. All right. Okay, so this is how we solve Boolean algebra. So this is an example question actually from quiz. So you can expect this kind of questions from your quiz also. Okay, so in my slides, I do have all this written down, so you can refer to them after this. Okay, but my scribbling will be gone as soon as I exit this PowerPoint. Okay, so I think like I'm not sure. If I scribble like this, I think it makes more sense. Because it's like step by step compared to showing you guys like everything like this. Okay, if you guys prefer everything in one go, you can always refer to my slides. I've already uploaded them before the class. All right, let's take a look at another example, and then we will end our class today. Right, is this the last example? Yeah, it is the last example. No, this is the second last example. All right, so let's try to do this one together, okay? Okay, let's try to do it. So we have over here A, B. Okay, let's take a good look at this equation over here first because like it's a longer one. Let's rewrite this into a bar form so that it's easier to see. Bracket, and then I have bracket again, A plus B. Okay, and then I have A plus C bar, correct? A plus B plus C bar, and then I close the bracket. And then I have this bar over here. Take a look at this. Bar over here is bar over the entire bracket. So if you would put it into bar, it will be like this, the bar over the entire thing. Okay, so and then it's like AB, and then you have bar as well. So I have this AB, B, and then you have a bar on top of that. Okay, cool, right? So that's why I like to write this bar because it's easier to see when you can where you can actually break it. Okay, now we see that this giant bar over multiple terms like this. Then let's start by breaking down the bar. That's usually the first step I do. So I'm going to write this back down over here. And then I'm going to break this giant bar into two portions. Portion number 1 and portion number 2. This bar and bar. Okay, big bar now becomes two smaller bar, but then I need to change the sign. So over here is a multiplication. Now I need to change it to addition. Okay, everything else is the same. That was what is in the bracket, and I'm just gonna write this down again. A plus B bar. Okay, so this bracket again. Now what about the outer bracket? The another bracket, we have this bar over here, and now we want to break it. So I'm gonna break this into individual bars. Now I need to change the sign, right? So this is a multiplication over here. Now I need to change this to an addition. Okay, so hopefully if you have a pen and paper, that hopefully you're following along up to this point. Okay, now let's take a look. What's the next logical step? So once you arrive here, we can see that, okay, the next logical step, okay, we still have this big giant bar across multiple terms over here. Okay, big giant bar is not what we want to see. Okay, we just don't like that because it complicates the situation. So let's just break this bar down. So let's break this. Okay, just gonna write this down. Okay, I like things to be tidy and neat so that I don't make any mistakes. So let me just write that one first. Now let's break this one. So bracket, still the same thing, bracket, okay. In this bracket, so let's break this. We have A bar and you have B bar. Okay, so the sign under this bar over here needs to change. So previously it was an addition. Now this time we have this multiplication sign. Okay, makes sense? All right, now the same thing over here. We have A bar, and then you have C bar, and then you have another bar on top because this one is the originally the bar is originally here, and we have this multiplication symbol sign changed. Okay, so now, okay, following, no error, okay, no error, okay, no error, no error. Okay, now let's proceed on to the next step. Let's write this a little bit more beautifully. So over here I have a bar, b bar, and I have over here inside a bracket, right? So I can limit its bracket, so it doesn't make a difference. And I have a bar, and then I have c. Double bar over here simplifies to just c. Okay, so this is what I have in my bracket now. And now we have a bar plus b bar outside. Okay, so now what we have over here is an opportunity for us to expand. Let me just do this bracket over here like that. Okay, so can you see the opportunity to expand over here? I just changed the bracket from square bracket to round bracket, right? So that it's like easier to see. Right, so let's expand this. Okay, let me write this a bit more neater like this. Okay, so then we can do this. So, okay, we're gonna have this one longer. I'm gonna start here. So we have a bar, b bar, multiply with a bar again. Okay, I can write this one, but you know that this a bar and this a bar is just a duplicate, so I don't have to write. If you want, you don't have to. So you can multiply this again. So you have a bar, b bar, multiply with b bar. So again, this is a repetition of the term, so it's redundant. So I'm just gonna repeat this. So it's still a bar, b bar, and I'm gonna write this here, a bar, c, and then I have a bar. So I'm just gonna eliminate this repeated term, and I have this a bar, c, and then I multiply it here with b bar. Okay, now this one there's no repeated term. Okay. Right, any problems with that? Let me double check again. A, B, A, B, A, B, okay. Okay, looks all right to me. Okay, now we see that, okay, this is like a repeated term over here. Exactly the same, so when we have exactly the same term, that's good news. We can eliminate that because it's a repetition. Okay, so I just eliminated this duplicate term. Now we want to apply some Boolean algebra laws to make sure this is simpler at least. So do you see what I see? Okay, do you see what I see over here? Okay, there is like a common term over here, and the common term is a bar c. So let's try to do something with that. A bar b over here, and I have here a bar c, and I can factor this out. This one becomes 1 plus b bar. Okay, remember this is our favorite term because this is 1. Okay, this is 1, and now we have over here a bar b plus a bar c. Okay, now can we factorize this out? Can we simplify this out again? So we can simplify this out. We can see there's a common term over here. We have a common term over here, a bar. We have a b bar plus c. Okay, so can we simplify this again further? I don't think so. Okay, so some of you might stop over here. Okay, some of you might stop over here and say that, oh yeah, there's no way to simplify this. But I go one step down further to simplify this over here. Because why? The reason why is because if you count the number of gates over here, so the number of gates over here is this one is one AND gate, there's another AND gate, and there's OR gate. Okay, so this like a bar, and this one is like b bar, and the other one is like a bar and c, and then they both go to a OR gate like that. Okay. How many gates over here? 3 gates. 3 gates. Now let's try this one. If we factor this one out, so it becomes OR gate, and okay, and becomes an AND gate. So this AND gate here takes a bar as the input, A bar, and it also takes like B bar, C. Okay, how many gates over here? 2 gates. Okay, so if you're a manufacturer, which one will you prefer? Of course, you prefer the one that has lesser cost. Okay, lesser gate means lesser cost. So this one is 3 gates. This one is 2 gates. That's like what, 30% savings over there from this this simple factorization of the terms. Okay, so that's why this one would be the final answer. Okay, is everyone clear on this?
Yes, sir. Very clear.
Okay, so hopefully things are clear. Now, let's take a look at one more example, and then we'll end our class today. So I realize that the class is slightly longer than usual already. Oh, it's 1 hour 30 minutes. My apologies. Okay, so let's do this real quickly, because after this, like we'll never see this Boolean factorization or this again. All right, so that's why if you have a pen and paper, I encourage you to do this together with me. All right, so this will be the last example of the class, and then after this, you have your quiz on the same topic. All right, so as usual, we determine the most simplified Boolean expression of this blah blah blah. Okay, so there's one more thing I want to explain over here. If you see this, f in bracket ABC, so it means that this ABC thing, they're all the inputs. Okay, so which means that there is no such thing as D. You will never encounter D inside here. Okay, these are all the inputs over here, A, B, and C. There's only 3, so that's why it's written in this way. Sometimes you will also see like this without this bracket over here. It's the same thing. If you just write F, it's just the same thing. Okay, again, F is just a letter. It can be X, it can be Y, it can be anything else. Okay, but you will commonly see F in textbooks, in maybe website, blog posts. Yeah, so that's what this F and this bracket is all about. So don't be alarmed if you see this. Okay, let's very quickly do this one, the last one. As usual, I would like to write this in overhead bar form so that it's easier to see which bar it can be broken. So we have A bar, and B. We have B, and then you have a bracket like that, and then you have a bracket like that. You have A, B, there's a bracket, smaller bracket, and there's a smaller bracket over here, A, B, and there's a bar on top. Okay, so then there is a big giant bar on top here. Am I doing this right? Do this with me. If you find any mistake, just please voice out, because I don't have the answer like in front of me, right? So that's why I am relying on you also to check my double check my works. A bar, okay, B, okay, this A bar, okay, bracket, big bracket, small bracket. Okay, so I figure out that I purposely do this without the answer in front of me, because this is how I would solve the problem. So I want you to see how I usually solve this problem, so that it also becomes the way you would solve this problem when you don't have an answer in front of you. So this is one strategy I use. If I have an exam, this is what I do. So I don't have the workings of everything else in front of me. I try to rely on what makes sense to do over here. Okay, so what's the first thing you see? What makes sense to do over here? So it makes sense to first break the bar, remember? So we don't like this large bar, because with this large bar, you cannot do any kind of operation with this large bar on top like that. So what you want to do first is to break all possible bars. So I'm going to write this down again. Let me just write this down. A plus B, okay, same thing over here. I'm going to keep this bracket, bar like that, bar like that, broken into two pieces. Okay, so broken this into two pieces. Okay, I'm going to write that here. Okay, this one needs to change. This one needs to change. Okay, so A and B, originally they already have a bar on top of both of them. So like this one bar goes on top of that. Okay, so no issues there, right? Plus, and this one sign changes. Bar broken on both. Okay, now let's take a look at what's logical to do next. And you know that this two bar, they cancel out one another, right? Okay, let's write this again. Okay, so this big bar. Now I'm going to break this one next. So we have A bar like that, and you have C bar like that, and this plus will turn into multiplication. Okay, so I have that bracket, and I have plus, I have AB. Okay, so the two bar cancel out. So if you want to write this more beautifully, you can write this as AC bar. Okay, let me just bracket this. I can write this like this, plus AB. Okay, makes sense. This bracket is redundant. Okay, then you have this outside here, plus B. Okay, looks good to me. Okay, now what's the next logical step over here? So the next logical step is to expand this. Okay, so let's try to expand this like this. A multiplied with AC, so we have A bar, C bar. Repeated term, I'm not going to write it again. A multiplied with here. So you have A bar multiplied with A and B. Okay, so when you add that to this, you have B, B multiplied with A bar, C bar, B multiplied A bar and C bar. And next you have this one, B multiplied with A, multiplied B. Okay, I'm not going to write that. Repeated term. Okay, so now, what do you see? So can we factor things out? Yes, we can factor things out. Let's talk about that after this. But there's one peculiar thing over here that we see. The weird thing over here is that you have A bar and multiply by A. So we know that this one is, what's this? Okay, if you cannot recall, let me show you the A bar multiplied with A, right? What is it?
0.
Yeah, exactly. So we have A multiplied with A bar. Okay, no matter what the value of A, it's going to be 0. So that is good news as well. This is also something we want to see. Okay, so when we have this to be 0, right? What happens? When we have this to be 0, the entire term will be 0 because it will be 0 multiplied by B, which also gives you 0. So this entire term will just be cancelled out like that. Okay, let's rewrite this. A bar, C bar. This one's gone. Plus, I'm going to rewrite this again so that it's clear. B. Okay, so do you see what I see? Again, this magical factorization like thing comes out again. So you can factor out this and factor this 1 plus B. That, and then it becomes AB. Okay, and this is good news. This one becomes 1. So at the end of the day, we have A bar and C bar, A bar and C bar multiply 1. Okay, you can have A, B. Okay, can we do any kind of simplification anymore after this point? A bar multiplied with C. I believe no. Okay, this is, I think, the final answer. If you can simplify this, do let me know. Okay, this is the final answer for this question. Okay, these two questions, I don't have the answer on the slide, so you have to rely on this recording and this scribbling. Okay, that is all for our class today. Any question, anything you're not clear with today before we end the class?
All okay, sir.
All okay? Okay, so.
All okay, sir.
All right, thank you for all your response. Really appreciate it. And again, this is the attendance. And if you have any question or you feel like you're a little bit shy, like please feel free to stay back after the class, and I will try my best to answer all of your questions. And as usual, I will release the quiz for today's topic after this. And as usual, we'll have 1 day for you to completely answer the quiz. Okay, if there's nothing else, I will see you guys again on Thursday class. All right, thank you, everybody. Bye-bye.
Thank you,
Take
sir.
care.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Sir, I want to ask regarding the project video.
Yes.
For the timing diagram, do we need to do in handwriting or in result of graph?
Result of graph, meaning to say you want to use Microsoft something, Microsoft Word or PowerPoint to do it?
No. I mean we use quarters like in the digital logic lab, or just we need.
I don't teach quarters in the lab, so I don't expect you to use quarters. But if you want to use quarters, I will not stop you. You can go ahead and use quarters if you want. Yeah, or if
So
you don't want to
if I
use
do in
quarters,
handwriting,
yeah, if you don't want to use quarters, you want to use any software, even if you do it in handwriting, I will still accept it because that is what I teach you in the class.
all right. Thank you, sir.
Okay. Anyone else with problem issues?
Thank you, sir.
All right, you're welcome.
Sir, can you
Yep.
hear me?
Yes.
Okay, this is my first class today. I just registered like last week on Thursday, Friday.
Oh, okay.
So I don't know what I'm missing. I just know that I took this subject before, but I had to drop it due to some financial reasons. So.
Oh. Okay.
So did they take test one like or midterms or when?
So so first thing first. Do you know how the team is structured? You have many channels, right, in the team. Are you aware of that?
Yeah, I know. I saw them. I was checking them yesterday.
So in my class, there will be no tests. There will be no final exam. I think it's easier. Not easier. It's more beneficial if you guys do some kind of a project.
Okay.
Yeah. So do expect some project during the midterm, and do expect some project during the end of the semester as well. And other than that, after every class, I would have like quizzes like this. So I would really need you to understand each class and answer the quiz.
Okay, and where can I find this quiz?
In the teams. Like after this, I will post the quiz. You'll get a notification saying that there is a quiz, and then like you will need to answer them.
Okay, so there will be no midterm or final. There will be projects.
Yeah, no midterm, no final. There will be midterm project, and there will be final project. I have posted the course outline as well if you're interested to know more.
Okay. Thank you, sir. Thank you.
All right.
And one last question about the previous lectures. Can I find them in the Teams, sir?
Yes, every single lecture is recorded. You can find them at the appropriate channel. So there is like channel for there's channel for topic 1, there's channel for topic 2, 3, 4, and so on. So
I see.
So that it makes it easier for you to look. If you want to look for topic 1, just go to the topic 1 channel, and everything is there. The video is there, the notes are there, all the suggestions of tutorial questions they're all in that channel. So I don't mix between channels, so that it's easier to search.
Okay, thank you. That's actually very good, sir. Thank you.
All right.
Okay.
You're welcome. All right.
Thank you.
All right. See you.
See you.
Bye-bye.
Bye-bye.